Hi guys, we're Math 8, Day 8. So today we're looking at 46, 47, 48 for our lessons. So 46 is solving problems using scientific notation. So again, we remember our powers of 10 and all of that. So how we can solve these, okay, we have what's known as our coefficient. This is our base 10. We always use base 10 in scientific notation, whether it's a positive or negative exponent. Another coefficient and another base 10. So if we're multiplying these, we're going to multiply the coefficients. 1.2 times 4 is 4.8. And then we remember our rules of exponents with the same base. 10 to the power of 6 times 10 to the power of 8. I add 6 plus 8 to get 10 to the power of 14. Make sure this coefficient is greater than 1 and less than 10. So we have a number in the ones place and then everything else to the right of the decimal. So it's got to be in that form. So we may have to manipulate some of them at the end. So let's look here. If I have 1.2 if I have 1.2 times 10 to the power of 5, 3 times 10 to the power of 5. So multiply my coefficients. Since we multiply in any order we want, we can do this. 1.2 times 3, 3.6. 10 to the power of 5 times 10 to the power of 5. 5 plus 5 is 10. Okay, this coefficient is still how we want it, so we are done. Okay, so that's what we are doing when we multiply scientifically notated numbers. And again, we could put this into our calculator, calculate out. It's going to give us probably a large number, which is okay. Is it the same as the form that we came up with right here? It should be the exact same number. And if it's not, then we know we did something wrong. So that's a quick way, especially on a test, that we can go back and check our work. Now, when we're dividing, we do the exact same thing. We divide our coefficients, okay, and then we look at our base 10, and we divide those, and remember that it's the same base, so we subtract those exponents. And we can express scientific notation even if we end up with a negative exponent. That's okay. We can leave it as is. So if I look at, let's look at C here. All right. So if I get 7.5 times 10 to the power of 6 over 2.5 times 10 to the power of 6. So I can divide my coefficients. And I could, again, move the decimal over kind of just mentally if I wanted to as I do the math. So 75 divided by 25 may be a little bit easier. Again, don't get too confused because we're working with decimals and we don't want to change the value. But 7.5 divided by 2.5 or 75 divided by 25 would be 3. 10 divided by, 10 to the power of 6 divided by 10 to the power of 6. 6 minus 6 is 0. So 10 to the power of 0 or 10 to the power of 0 is just 1. 3 times 1 is 3. So 3 is probably not a number that we would normally put in scientific notation because it's a whole number. We usually use scientific notation for really large numbers and really small numbers. But again, we could simplify this down to where we have it just as 3. All right, so we'll look at these practice problems, get comfortable with multiplication and division as we go through. Again, some of them might be, we might be given a word problem, have to express it in scientific notation. Just remember the coefficient is between 1 and 10, so we can't have anything in the tens place. We can't have everything to the right of the decimal. We have to make sure that the coefficient is written correctly. And as we move the decimal, if we move the decimal to the right for a number, then we have to take 1 away from the exponent. If we move it to the left, then we have to add 1 to the exponent. So just pay attention to that, so we're not just moving decimals without keeping it equivalent to the same number. All right, 47, we're looking at graphing functions. Again, we've worked with linear functions, the most common one we'll probably see, but there's all sorts of functions. As long as it passes the vertical line test, and for one input, there's one output, then we know it's a function. If it doesn't pass the vertical line test, then it's not a function. So again, we talked about our x values, which usually we use x and y because we plotted on the x and y coordinate plane, but that's our input or a dependent variable. And then our output is our y values or our output or our dependent variables. That's usually what we put in as y. And so we put in x, our input, we get our output, our y values. A domain, again, highlighted word right here, that refers to all possible inputs. Okay, so what numbers are possible on that? And then range is all possible outputs. So if we look at our own example like this, if I have a graph like that, I know it's terribly drawn, but these are my y values, this is my x-axis. So x continues on forever this way and this way. So really x values would be all numbers between negative infinity and positive infinity. But if it starts, the y values start at 1 here and then go up, I can't say all numbers because -1 or -2, 3, whatever, or even 0 for this example, would not fall on this function. So all possible range values would be 1 and above. And we'll show you how we would represent that numerically, but just be aware that's what it's referencing. So all possible x values would be domain and range. I just remembered d for domain, x, dx for whatever reason. So domain is our x values, and then range are all possible y values. Okay, so if we look at example 1, the sign on the right describes a function. Okay, it's parking, $1 for the first hour, 2 for each additional hour, $15 maximum. It's open 6 a.m. to 10 p.m., no overnight parking. If you've been in a big city or seen a parking garage or lot or something, they probably have something like this. So what's the domain of the function? What is the range? And then graph the function. So again, domain is all possible x values. Okay, the domain of the function is the number of hours a car can be parked in the lot. Since the lot is open from 6 a.m. to 10 p.m., that is 16 hours. 7 a.m., 8 a.m., 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 16 hours. So that's the most that it can be parked in the lot without getting towed or fined or whatever. So 16 hours, that would be our domain. Now the range is the number of dollars charged for parking. So we know that it's $1 for the first hour, 2 for each additional hour, or part thereof, $15 maximum. So we know it can't go above 15, so it can go $1 for the first hour, then the next hour, because they don't charge you by the minutes, per hour. So $3 plus 2, 5, 7, 9, 11, 13, 15 would be where it would max out. So we can't get charged more than 15. So that would be all the possible output values, or that would be our range. Okay, and then we could plot this on the graph. Okay, right here. Okay, our x values, or our domain, our range, which is our y value. So time is the independent variable because we get charged after we know our time. How long we park there determines how much we pay. So that's why time is on the x-axis and change, or the dollars, is on the y-axis. Okay, if we have P equals 4S, this is probably perimeter of a square. 4 times the side length equals the perimeter. Well, what is the domain? Okay, and if we're talking about an actual square, so I may have jumped ahead for that's an actual square, we can't have negative side lengths. But if the function doesn't tell us what it represents, and we have to consider negative numbers as well. So we can plug in 0 for S, 1, 2, 3, 4, 5. We can do -1, -2, -3. So S is our input or our X value, what we would normally put it as. And then P is our Y or our range. So we can put in all positive real numbers in this case. Okay, if it wasn't referring to a square and it was just y equals 4x, and we graph that, then yeah, we would have negative numbers as well. But if it's just perimeter of a square, then it's all real numbers. Okay, it would go through the origin, because if we have a 0 side length, our perimeter is 0. 1, then it's 4. 2 for a side length, then it's 8. 3, 12, and so on, continuing on that. The range, okay, well, okay, if it's 1, it's 4. If it's 2, it's 8. Or we could have the side length is 1/4, then the perimeter would be 1. So it doesn't necessarily just have to be whole numbers. It can be all positive real numbers. So that would be the range. Okay, we can't have a negative perimeter. Okay, the table that we would make, again, we do our X, or our input, and then our output, or our Y values, or in this case, P, over here. Whatever's dependent, we put on the right. Our independent, we put on the left. So 1, 4, 2, 8, 3, 12, 4, 16, 5, 20, and continuing on, so on. Now, if we graph the function, we just go over 1 up 4, over 2 up 8, over 3 up 12, and so on. And since it's linear, we really only need 2 points, but we can make life easier and do a couple more points than that just to show the shape of the graph. Some other terms that we have. Okay, a continuous function. Notice example 2 is different from graph 1. The graph in example 2 is not interrupted with gaps. This means it's a continuous function. So the first one, the parking lot example, they didn't charge us. It was every hour, and it was a set $2. So even if we went 1 minute into the next hour, we got charged for the full hour. So it was just dots along the graph. Whereas the 4S graph, it was all connected, so it would be a continuous function. There's no breaks in it. The two functions together, these two features indicate the function is directly proportional. So for a function to be directly proportional, it can be a function and not be directly proportional. But if it's directly proportional, it has to go through 0, 0, or the origin, and it needs to be linear. So if it's got some sort of J or U-shaped or something like that and goes through the origin, it's not directly proportional. If it's linear but it doesn't go through the origin, then it's not directly proportional. So if we looked at a graph, okay, here's our origin. If we have a line coming out of there, this would be directly proportional. If we had something like this, even though it's linear and it looks the same, it's not going through the origin, so this one would not be directly proportional. Still a function, still a line, but it's not directly proportional. Okay, and then we will look at these practice set problems together. Okay. And then lesson 48, we're looking at percent of a whole. Again, the whole would add up to 100%. Okay, so Shanna answered 92% of the questions correctly, got an A on the test. Basketball player shot 80% of her free throws, so pretty good percentage. The governor was elected with 56% of the vote. Okay, so those are different percentages. All the free throws would add up to 100%. All the test questions would be 100%. All the votes would add up to 100%, hopefully. All right. Example 1, 30% of the students ride the bus. If 210 do not ride the bus, how many students are there in all? So again, just like we set up when we had a ratio and the actual count, we're going to do the same thing here, but we'll have our percent. So if 30 ride the bus, or sorry, 30 Yeah, ride the bus. We know, well, you either ride the bus or you don't. So that means 70%, even though we weren't told that, we can pretty easily calculate that 70% do not ride the bus, and it always totals up to 100%. Our actual count, we can use A for bus. 210, we were told 210 do not ride the bus, and then we were given a total. So we set up our ratios. 70 over 100 equals 210 over T, 70 over 100, and 210 over T. Cross multiply, I get 21,000 equals 70T, divide by 70. The total number of students equals 300. Then we could go back and find the difference to calculate A pretty simply, or if we wanted to do ratios again and cross multiply and divide, we could do that as well. But we were just asked for the total. Okay, Shanna correctly answered 17 of the 20 questions on the game show. What percent of the questions did she answer correctly? Okay, so 70. Let's get. And you can do either or percent and actual and percent. It doesn't matter. Just make sure they're lined up correctly. So we were told that she answered 17 of the 20 questions correctly. So we'll call correct, wrong, total. So she got 17 of the 20. 17 plus 3 is 20. She got 3 wrong. We weren't told that, but we can easily calculate it. Our total percent, well, there's 100% of the question, so the total is always 100%. And we want to figure out what percent of the questions did she answer correctly. So we want to know how many did she get correct. So let's set it up 17 over 20. Okay. And since 17 is in the numerator, we want C to be in the numerator. 20 is in the denominator, so we want 100 to be in the denominator. Cross multiply, I get 20C equals 1700. Divide by 20. So I do 1700 divided by 20, and that gives me 85. No, sorry, you can't see that. So 1700 divided by 20 equals 85. So that's the percent we were looking for. Got 85% correct. Another thing, since we know 17 out of 20, and you'll get really good at this when you're calculating, let's use an example from our test. Most of our tests are out of 40 points. So let's say you got 34 out of 40. Well, what's my grade on this? I'm going to tell you to calculate itself. Now we can go through and say 34 was correct, 40 was the total, 100% is the total. We can set it up like that. What I do is I think it's a little bit easier as I just do 34 divided by 40, since it's 34 over 40, and that gives me 0.85. And then if I want to know that as a percent, I just multiply by 100, or I just move that over 2 decimal places. So if you got 34 out of 40, you got an 85% on your test. And so I think that's pretty easy calculation. Once you know the number right out of the total questions, you can just perform the division and then move your decimal, and you have your percentage that you got. Okay, we'll take a look at this practice set problems when we return to class. Okay, just set up your ratios like you would your percent and your actual count, fill in what you know, and cross multiply and divide. All right, we will see you guys in class.